So far, we've looked at examples of a blending tank, a heated tank, a reactor, a bioreactor, and an absorber. In all 5 of these examples, we've assumed that the material is perfectly mixed, or in the case of the absorber, at least within each stage, the stage was perfectly mixed. Sometimes we want to model chemical and biological processes for which important process variables like concentration and temperature vary continuously in some dimension. If we want to discern the spatial variation of important dependent variables, then we're probably going to have partial differential equation models. Consider this example of a double pipe heat exchanger. An important dependent variable of this model might be the temperature of the liquid flowing through the interior pipe. The temperature of this liquid might be a function of both time and position. If we assume that there is no axial conduction, that the tube wall temperature and the process fluid TL temperature are functions of time and position, the temperature TS, that is the temperature of the heating steam, is a function of time only, and that the fluid has constant fluid properties, then we can obtain a PDE model by beginning with a shell balance on the liquid. Here, the 2 independent variables will be time and the axial position z. Within a differential volume element, represented by a differential length, delta z, down the axis of the pipe, the accumulation of thermal energy is the rate at which thermal energy enters and leaves the differential volume element, where S here represents the cross-sectional surface area that the liquid is flowing through, and V sub L represents the velocity of the fluid in the z direction. The thermal energy entering or leaving across the tube wall is given by this term. Dividing this equation by delta z and taking the limit as delta z goes to 0 gives us a PDE model for the time and position dependence of the fluid temperature. Similarly, we have a PDE model for the temperature of the wall. If we were to assume the system were at steady state, then these equations would be a first-order ODE for the temperature of the fluid and an algebraic equation for the tube wall temperature. The transient equations, however, are coupled PDEs, which require 3 boundary conditions to solve. For coupled PDEs, numerical solutions are likely required. To summarize what we learned from Chapter 2 of the Seaborg text, we articulated steps for developing theoretical models that usually yield systems of ODEs. We looked at a blending example, which gave us the opportunity to review the degree of freedom analysis, how to assign output variables, disturbance variables, and manipulated variables, and we considered some modeling alternatives, such as gravity-driven flow. Then we considered the heated tank example, which allowed us to review energy conservation and options for parameterizing the heat flux term, where we wrote energy balances around a heating coil. Then we looked at general balance equations for mass conservation, energy conservation, and species mole balances. When modeling chemical and biological processes, we can always start with writing these balance equations. These often need to be supplemented with additional equations, such as rate equations for chemical reactions, equations of state, vapor-liquid equilibrium, and we showed examples of all of these. The CSTR example showed us how we can model a process using coupled material and energy balances, and the fed batch bioreactor was an example that involved multiple species balances. The 3-stage absorber provided us with an example for material balances for the same component coupled at 3 different points or 3 different stages in the process. And the double pipe heat exchanger is an example of what we call a distributed parameter model, one that has position as an independent variable, and these often result in partial differential equations. All of the basic methods and principles of modeling chemical and biological processes that were reviewed in chapters 1 and 2 are things that you're already familiar with from your previous CBE courses. The reason that they're reviewed here is to solidify these methods, provide you with some common notation that we will use throughout the semester, and to emphasize that these theoretical models are very important, and to emphasize that we'll use these types of theoretical models when designing control systems for the rest of the semester. So you should be familiar with how to develop and analyze all of these types of process models. So you should be comfortable with developing and analyzing process models with the features that we've reviewed here. All of the basic methods and principles of modeling chemical and biological processes that were reviewed in chapters 1 and 2 are things that you're already familiar with from your previous CBE courses. The reason that they're reviewed here is to solidify these methods, provide you with some common notation that we will use throughout the semester, and to emphasize that we'll use these types of theoretical models when designing control systems for the rest of the semester. So you should be comfortable with developing and analyzing process models with the features that we've reviewed here.